and a very warm welcome to our 2025-26 season of talks from Guildford Astronomical Society. This is our 70th anniversary year, so it's a very special year for us, and we've got some very exciting talks coming up. Today, we've very pleased to have Professor Andrew Coates coming to talk to us about the search for life on Mars. We go on to the next slide. Basically, for anybody who's not familiar with Guildford Astronomical Society, and I should ask, who is new today? Who has not been to a meeting before? Oh, fantastic. You are extra welcome. Lots of new people today. So we are a friendly society. We're a very active society. We organize lots of activities, including these regular talks. If you're a member, we do stargazing. We do outreach events as well. We also have a very active imaging group. If you like imaging, you can get to whatever level you like, and our members have had images published in all sorts of publications. And basically, everyone is welcome if you want to join the group or you just want to come along to these talks and listen to our speakers. Do the next slide. So, as I said, it's our 70th anniversary. There's the wonderful cake that Julia baked for us. More after the break. We have some photos from our little party that we had. That's the cake before we started on it, actually. So today's meeting, we have Professor Andrew Coates. We'll then have some questions. Then we'll have a short break. There's tea and coffee outside for £2. And after the break, Julia will be talking us through what's up. Our librarian, Matthew, will be talking us through the wonderful selection of books we have to borrow. Rachel, I believe, will be here to talk about outreach. She's here. I can see her. Oh, welcome, Rachel. And also, I'll be showing the party photos and talking about our next season of talks. And by the way, I would mention we do have leaflets down the front, which list all the talks, or they're also up on our website if you want to look at our website. So feel free to take a leaflet if you wish. We've got plenty of them. So next slide. Oh, so we have Professor Andrew Coates, and this is where I refer to my phone here. So Professor Andrew Coates gained a BSc in physics from UMIST in 1978, MSc in 1979, DPhil in 1982 in plasma physics from Oxford University. He's been UCL's Mullard Space Science Laboratory, MSSL, which is very local to us, since 1982, with temporary guest positions at Max Planck Institute for Solar System Physics in Germany, the University of Delaware, USA, and the BBC World Service Media Fellowship. He's now Deputy Director, Solar System at UCL MSSL. His space mission involvements include the Rosalin Franklin ExoMars Rover, where he leads the PanCan team, Cassini, where he led the electron spectrometer team, part of the Cassini plasma spectrometer, Venus Express, Mars Express, and Giotto. His scientific interests include the solar wind interaction with planets and comets, planetary surfaces and space instrumentation. He's authored and co-authored over 580 publications, including over 460 referees. He was a member of the STFC Science Board. He's active in space and science outreach via public talks and media. He was president and vice president of the Society for Popular Astronomy and delivered lectures at Gresham College. Professor Coates.
Well, thank you very much, Richard, for the kind introduction, and I need to mic up. Okay. Hopefully people can hear me. Is that okay? Yeah, good, perfect. Okay, so I'm going to talk about looking for life on Mars, and I'm from, oh.
I'll get you the right screen.
Yeah. Do I need to do anything?
Hopefully not.
Hopefully not. That's good. It was in full screen before, but okay, very good. Okay, yes, perfect. So yes, so I'm at Mullard Space Science Laboratory, part of UCL. So that's about 12 miles away from here in the middle of the Surrey countryside. And Julia was there for several years, up until a couple of years ago. Yes, I'm Deputy Director in charge of the solar system. The other Deputy Director is in charge of the rest of the universe. So between us, we have it covered. But I deal with the solar system, which is where we live, and where there's some interesting stuff as well as the more remote objects. But yeah, so looking for life on Mars. In the background there, you can see a picture of our rover. Now, this is not a real picture, it's a computer-generated picture. We had hoped to have real pictures of our rover on Mars. We were expecting to launch that in 2022, but unfortunately, due to geopolitics, it was not launched because it was a collaboration between the European Space Agency and the Russian Space Agency at that time. So we now have to wait until 2028 to launch this. But I'm going to be partly talking about that and partly about looking for life on Mars in general. So as Richard mentioned, I'm principal investigator for the camera instrument on this. This is the PanCam instrument, which is at the top of the mast there. The whole rover is about, that's 2 meters off the ground on Mars. The whole thing weighs about 300 kilograms, so sort of golf buggy size, that type of thing. Solar powered, as you can see from the solar panels. And we'll be drilling underneath the surface of Mars for the first time with this to a reasonable depth with this rover. And we'll tell you about that as we go. So all we need to do is change the slides. Right, good. Right, so looking at the top locations for life beyond Earth. So Mars is one possible, and I should say, start off by saying for people maybe unfamiliar, we don't know of life anywhere else than Earth at the moment. Nowhere else in the universe, not in the solar system, not anywhere else. So the search for life elsewhere, are we alone or not? This is one of the key questions for humankind. But there are some places in the solar system where there could either have been or could even be life now, and those are sort of pictured on this slide. So on the top left we see Mars, which we're mainly talking about tonight. As you can see, that's smaller than the Earth. It's about half the size of the Earth in terms of diameter, which means it lost its heat of formation at the beginning of the solar system, which was 4.6 billion years ago, lost that heat of formation more quickly than the Earth did. And that had some consequences, as we'll see. But this is one of the possibilities for potential life elsewhere. But there are some other places in the solar system as well, which it's worth mentioning as possibilities for life. So one on the bottom left there is Europa, one of the moons of Jupiter. So this has a subsurface liquid water ocean underneath its icy crust. We know that from previous missions to Jupiter, which have had magnetometers and other instruments on board, able to look at the structure a little bit of Europa. But we have the JUICE mission on the way, and also the Europa Clipper mission, which is also on its way to look at Europa later in this decade and beginning of the next. But Europa is one of the places in Jupiter's system where there could be the possibility of life even now. So it has liquid water, it has other conditions which may be right. Unfortunately, it's buried in Jupiter's radiation belts, very intense radiation belts which Jupiter has. But underneath the surface is that ocean. And there's the idea of potentially even being life in that ocean. It's a primitive type of life, perhaps. Another one on the top right, this is Enceladus. So this is one of the moons of Saturn. We were involved, as was mentioned before, in the Cassini-Huygens mission. So Huygens, the European Space Agency probe, which landed on Titan, the Cassini orbiter orbited Saturn for many years, from 2004 to 2017. And we were lucky enough to have an instrument on board that NASA orbiter measuring electrons. One of the amazing discoveries in the Saturn system was that not only is Titan interesting, but also Enceladus. Enceladus again has a liquid water ocean. It orbits relatively close to Saturn, a little bit like Europa in the Jupiter system. It orbits about 4 Saturn radii away from the parent object, and it has a liquid water ocean. So So this was discovered initially by the magnetometer on the mission, which discovered a wiggle in the magnetic field data, and that we were able to take a closer look at Enceladus and actually found that Enceladus has these tiger stripes, which you can see the blue stripes there at the south pole of Enceladus. Those are the source of plumes which come away from Enceladus, and so that is bringing the water from the subsurface ocean and also other stuff with that out into the Saturn environment. And we were able, with Cassini, to fly through that several different times. And in fact, the mission was changed a bit to fly through it a bit more because this was such an interesting discovery. We were effectively flying through material directly from the subsurface ocean, so able to look at the composition. So what was found was things as well as water, which we found with our instrument as well as the others. So we found negative ions associated with water in the Enceladus plumes, and going along with the magnetometer measurements, but also things like sand. Silicon dioxide was found. So that may be from subsurface vents, perhaps underneath the ocean, and also other materials were found. So and the possibility of there being life at Enceladus now is certainly a possibility. We have the right conditions there too. So Europa and Enceladus are definitely good places to look, as well as Mars, for signs of potential life. Also Titan, towards the bottom in the middle there. So Titan is one of the moons of Saturn, the second biggest moon in the solar system. It's the only moon which has got a significant atmosphere. So none of the others, Europa has a very weak atmosphere associated with bombardment of the surface by particles from Jupiter's radiation belts. But Titan has a really significant atmosphere, and that's 1.5 times the pressure of air in this room. So 1.5 times the Earth's atmospheric pressure. It's made of nitrogen and methane, so a very interesting atmosphere. And in fact, initially, with the Voyager missions, which passed, one of the Voyagers which passed Titan, that was shrouded by haze in the atmosphere. So people thought this was interesting. So with Cassini-Huygens, we had ultraviolet and infrared, so we could peer through and look towards the surface. And the results of that are shown in this image here. So Titan has that interesting atmosphere. With our little instrument, we discovered prebiotic chemistry going on in the upper atmosphere. So that was one of the amazing discoveries from Titan. But Titan now is too cold really to support life. The surface temperature is 93 Kelvin, which is the triple point of methane, so it's minus 180 degrees centigrade, something like that. So really cold, and so people think that there's not the possibility of having life on Titan now. But that prebiotic chemistry means there's the ingredients. So in about 4 billion years, when the sun explodes, becomes a red giant, it will engulf the Earth, and it will heat up the outer solar system. And Titan is one of the places where potentially life could start there, perhaps at some point. So also on this slide is Venus. So a few years ago, a colleague, Jaden Greaves from Cardiff University, found phosphine in the Venus atmosphere. That's a controversial result still. There are some people, some evidence which seems to support that, some which does not. So it's not a definite result. But if there was phosphine there, that's indication of phosphorus, which is one of the ingredients potentially for life. But there are other processes which could produce that as well. So Venus, people think that there's not really the possibility for having life in the clouds of Venus. You can see the clouds there on the slide. The clouds are made of sulfuric acid, and it's in those clouds where there's also water and also potentially this very small amount of phosphine that people thought, well, maybe there's the possibility of life there as well. So we've kept it on the slide for now. And also at the bottom, as a sort of throwaway comment, of course, extrasolar planets, that's another place to look for potential signs of life. And so there are missions which are going to do just that. So the aerial mission, for example, which will be looking at atmospheres of extrasolar planets and looking for life signatures in that, will be very exciting in a few years' time. And there are many other missions, including Habitable Worlds Observatory, which hopefully we will, later on find signs of Earth-like planets elsewhere. There's also Plato being launched next year, but that's not doing a direct measurement of the atmospheres. So there are other places in the solar system where there could potentially either have been or may even be life. And we're talking about Mars tonight, so we'll concentrate on that for now. So why do we think there might have been life on Mars? So it's 3.8 billion years ago, Mars was a very different place. And on the left-hand side, this is an artist's impression. It's not actually a simulation, but it's consistent with the simulations. Of there being water on the surface of Mars, which we found evidence with orbiters and rovers for that, and other substances in the atmosphere, but water on the surface, water in the ice caps, water in clouds on Mars. We think that was present 3.8 billion years ago. So I mentioned the solar system started 4.6 billion years ago. So this is a long time ago in the solar system's history, 3.8 billion years. So what changed? Something changed to actually change that, that environment, which was potentially habitable at that time, to what Mars is now on the right-hand side. So Mars now, a very desert-like planet, very little atmosphere, less than 1% of the Earth's atmospheric pressure, a very cold surface because of that lack of atmosphere. So on the day side of Mars, it's maybe 10 to 20 degrees, depending on where you are. And then or 0 to 20, and then at night, though, it goes down to minus 100 to minus 120 degrees centigrade, so very cold at night. So anything you put on the surface has to survive all that. So very cold, a very thin atmosphere. So that means that the surface is bathed in ultraviolet. So it's like being under an ozone hole all the time on the surface of Mars. Also, radiation from space, from the galaxy, and also from the sun, solar energetic particles can get through to the surface. So the radiation environment on the surface is not good for life. So something changed between 3.8 billion years ago and now. And what changed is that suddenly, at about 3.8 billion years ago, after the sort of late heavy bombardment going on at that time, Mars lost its magnetic field. Now, we think that's because Mars was cooled off more quickly than the Earth did. So the Earth kept its magnetic field. We still have a magnetic field, but Mars was basically frozen. The dynamo was frozen, and so Mars lost its magnetic field. And if you lose a magnetic field in the solar system, that means that the solar wind, which is material coming out from the sun all the time, can strip away your atmosphere. And that's what happened with Mars. So that's why Mars now has sort of less than 1% of the Earth's atmospheric pressure. It's a mainly carbon dioxide atmosphere, so not habitable. But 3.8 billion years ago, we think there's a chance that Mars was habitable. So what's the evidence for that? So the evidence is from lots of different orbiters and indeed landers and rovers which have been to Mars. And this is just one example. So on the top left, we see evidence for water on the surface of Mars. This is an outflow channel where water in the past has flowed across the surface of Mars. There's evidence for that by looking at the minerals and so on, which are associated with that. Things like clays on the surface. There's lots of evidence for water having played a role on the surface of Mars 3.8 billion years ago. It can't support that now because the pressure is too low, the atmospheric pressure is too low, the temperature is too low, so we can't have, or at least we can't have, because of the pressure, we can't have water in the liquid state on the surface of Mars. But 3.8 billion years ago, there's lots of evidence. So this started with the Viking missions in the 70s of seeing signs of outflow channels and so on the surface of Mars, which, and this particular image is from Mars Express, and you can see a sort of sinuous outflow channel associated with Mars's history. So the other thing is that Mars had this magnetic field. So I mentioned this already. Mars lost its magnetic field. How do we know that? We know that the evidence for that is that the first magnetometer thing which can measure a magnetic field, which was sent to Mars, was in the early 90s. That's Mars Global Surveyor, one of the US missions, that had a magnetometer on it. And the map here, this is a map of Mars with latitude and longitude in the normal way. But the colors give you height above the surface of Mars. So going from blue, which is very low locations, through green, yellow, red, and ultimately white, which is the highest locations here. So we have the volcanoes, Olympus Mons and Tharsis region volcanoes here as well. So we can see the northern hemisphere is relatively low, the southern hemisphere relatively high. And what's plotted over this actually is those magnetic field measurements. And we can see the black and white contours. This is outward and inward directed magnetic fields. And these are parts of the surface, especially the southern hemisphere, which is very cratered. And we know from the cratering density, it's about 3.8 billion years old. So this is the time the rocks were forming and it actually trapped magnetic field. And so that's the evidence for Mars once having a dipole magnetic field, just like the Earth does. So the Earth now has a magnetic field. We used to use it for navigation and so on. Now we, use GPS and phones and so on. But the people doing Duke of Edinburgh still do using compasses and so on. So so we have the magnetic field on Mars, and this is the evidence. So these crustal magnetic fields are relatively weak, but they're there. And so with the Mars Global Surveyor mission, this was the evidence that Mars once had a magnetic field which would have protected its atmosphere early on. So the other thing which it had 3.8 billion years ago is volcanism going on. So this is an image of the largest volcano in the solar system, Olympus Mons, 600 kilometers in diameter, about 27 kilometers high. So it's 3 times the height of Mount Everest. Huge object in the relief, and you can see that on the map is here. But this is the image of it on the bottom left. But it's extinct. So there was volcanism as well as a magnetic field going on at that time, and that would have given a cycle of things like carbon and water and things like that at the time, just in the same way that the Earth is still going with that now. So it contributed to cycles of those things. So everything was right 3.8 billion years ago for it potentially to be habitable. So if we just take a step back and think about what we need for life, the requirements for life. So liquid water, we've mentioned that as important. We also need the right chemistry. So it's things like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's where that phosphine came in as being important on Venus, that P. We need a source of heat, and we need enough time for life to develop. So that's the sort of recipe for life anywhere else in the universe. And we think that was present on Mars, or at least the evidence shows that should have been met around about the time. What we're not sure of is if there was enough time in that situation for life to develop. But interestingly, that 3.8 billion years ago, 3.8 to 4 billion years ago, is when life was starting on Earth. So if we had the right conditions on Earth, right conditions on Mars at the same time, we may have had either separate genesis of life or some other type of thing which would have needed collisions. But there's the possibility of life starting on Mars at that time. So early Mars is a possibility for life to have been there. So there's lots of interest in Mars, of course, lots of space missions. You can usually launch roughly every 2 years to Mars because of the way that the planets line up. Mars's year is just over 2 years of Earth. And so every couple of years you can launch. So in 2020, there were some important launches. So the UAE launched the HOPE orbiter. That is still looking at the atmosphere of Mars and looking at the aurora, which was discovered actually with the Mars Express mission a few years ago, but it's looking at that. Also, China launched the Tianwen-1 orbiter and the Zhurong rover, which landed first time and worked. And so the orbiter is still sending back important information about the Mars environment. NASA launched the Perseverance rover and the Ingenuity helicopter, which we'll talk about a little bit in a minute. So 2022, which would have been the next opportunity after this, was when we had hoped to launch Rosalin Franklin, which again you can see on the right-hand side there. but because of the Russian invasion of Ukraine, we weren't able to launch. As I say, we were hoping to use a Russian rocket, a Russian landing system, and some Russian radioactive heating units on the rover to keep it warm at night. We weren't able to use any of that, and so we're now hoping for support from the US, and which looks very good that we will get it. Fingers crossed. So 2022 would have been us, and unfortunately wasn't. So 2024 would have been the next, but actually there was a delay with this mission, Escapade, which is now due to be launching later this month, actually. I think 29th of September is when that mission should be going. That's to look at the space weather on Mars. It's a 2 spacecraft mission, which will hopefully do that. And launching in 2025 on a high energy trajectory, which you can go a slightly different way to get to Mars, despite being slightly out of the normal launch sequence. Next year, Japan is launching the MMX. That's a sample return for the moon Phobos of Mars, which will hopefully bring samples of Phobos back to Earth, which will be very exciting to get and look at in Earthbound laboratories. And in 2028, that's when we now hope to launch Rosalin Franklin. Again, this is pictured on the right. And there are several missions also still working here, which are shown at the bottom of the slide. So lots of interest in Mars. And of course, Perseverance, we can't not mention that. So Perseverance, amazing mission from NASA, which landed with a sky crane system. It's a 1-ton rover, so bigger than Rosalin Franklin. It's also nuclear powered. And this is a selfie of that on the red planet, successfully landed. And indeed the Ingenuity helicopter on the left-hand side here, which you can see quite nicely there. So that combination is on Mars now and sending back amazing data. And in fact, the helicopter is interesting. This is the first time a helicopter had been tried on Mars. You can see this is a movie actually taken from Mars CAMS-E, which is one of the instruments we're involved in on the rover. So this is the helicopter here taking off on Mars for the first time. This is no mean feat. I mean, in that very thin atmosphere, you have to have very rapidly rotating blades, 2,400 RPM. So it went up successfully. This was its first flight. This is like a Wright brothers moment on Mars, you know, actually being able to fly for the first time in a controlled way and then land again successfully. In fact, it's quite amazing. It actually took about a square centimetre of the Wright brothers' first plane that they flew at Kitty Hawk, which I was lucky enough to visit myself earlier this year. So Perseverance has done some amazing work on Mars. So as of today, this is where it is. Perseverance has travelled 39 kilometres on the surface of Mars. And to give you some context here, that around the side here, this is where there's a big crater rim called the Jezero crater. This is where Perseverance landed. It landed a little bit away from this river delta. You can see there's on the left-hand side, this is where water used to flow in 3.8 to 4 billion years ago into this crater. And you can see there's a nice delta here, which the Perseverance was able to look at in detail. On the other side, there was an outflow channel as well. So we know that this crater was full of water. There's lots of signs of clays on the surface from mineralogy, especially done with Mars Express, Europe's Mars Express mission. So what this mission was doing was collecting samples, which will hopefully be brought back to Earth. So far, something over 20 samples have been taken. The numbers are here. But the helicopter itself was only designed to do 2 or 3 flights on Mars. It actually did 72 flights. Its last flight actually was in January last year, and then its rotor, is not able to fly anymore. But very exciting mission, and we hope that these samples will eventually be brought back to Earth. That's the idea. So the rover has been roving around, looking at that, especially at the river delta, but also the crater rim. It's now up on the crater rim. This was its landing sequence. A number of you, I'm sure, saw the video as this landed, and indeed the stills from it as well. Very impressive, using the sky crane. So these are the actual tethers which the rover descended on and was placed on the surface and then cut the umbilicals and then fly away the thing into the sunset, literally. So that was an amazing landing. Second time that had worked after the Curiosity mission, which also landed in the same way and is still there making amazing measurements as well on the surface of Mars. But Perseverance is collecting samples. So this was the first sample which Perseverance actually took. Some of them these are stored in the rover, others in a cache region, which hopefully in the future we will have a mission to go and pick those up. So we've been talking about Mars sample return for a while. So Perseverance here, this is the thing which has been collecting the samples. We hope that there will be an Earth return orbiter and a sample retrieval lander, perhaps, which is this lander system. This may be the first powered rocket from another planet as well, so to actually bring the samples to the orbiter and then eventually back to Earth. But there's some budget issues in the US at the moment, and we hope that they will get through those and we'll be able to launch that mission in a few years' time. The latest date I heard was 2035 that people are aiming for now for that, but it's subject to some decisions being made right at the moment. But Rosalin Franklin is going, we hope at least. So we're looking for life on Mars, launching in 2028 and landing in 2030. So normally it takes about 9 months to get to Mars with the trajectory that you would normally use, 6 to 9 months, depending on exactly the launch opportunity. In this case, we're taking 2 years. So we're going to let it actually go around the sun a couple of times and then land after the dust storm season on Mars. That's the idea of that. You save some money by launching a little bit early, so 2028 it also is a better launch opportunity than the next one in 2030. So it gives us the chance of launching more payload. So we hope to be able to get that to the surface in 2020. So the really new exciting thing about this particular mission is we're drilling up to 2 meters underneath the surface. So the current Perseverance mission and also Curiosity are drilling sort of 6 centimeters underneath into rocks and on the surface. With Rosalin Franklin, we'll be drilling 2 meters, and I'll tell you why that's important in a minute. But we have a set of context and analytical instruments. But while we're on the picture of the rover, I'll maybe run this again. This is the rover. It was actually built at Airbus in Stevenage, so around the M25 from here. Thales Alenia in Italy are the prime contractor. Solar powered, these are the antennas to do with the subsurface sounding radar. The black thing on the front is the drill. PanCam, our instrument, is at the top of the mast, and there's an infrared spectrometer just next to that as well, which I'll also talk about. These are setting the context for the mission. So very exciting, and we're launching with lots of UK involvement in this in 2028. So why do we call it Rosalin Franklin? It's named after this amazing X-ray crystallographer called Rosalin Franklin, who did a lot of work, especially the work associated with the structure of DNA. So she was an X-ray crystallographer that's using that type of imaging to be able to look at the structure of DNA. And this was her most important image, photo 51 as it's called, which helped to actually discover the double helix of DNA. So it makes it a really important thing for basis of life. And so this is why the mission was called Rosalin Franklin. So because of the large UK involvement in this, the UK Space Agency had a competition a few years ago to name this rover, and Rosalin Franklin came out as the really good choice. There were other things like Rover McRoverface and things like that, were suggested, but those were thankfully not selected. But Rosalin Franklin is absolutely the right person to be naming this after. So she unfortunately died young and wasn't able to share in Watson and Crick's Nobel Prize for the discovery of the double helix. So, but we're naming the rover after her to keep that memory alive. Okay, so why do we need to drill 2 meters? Well, we need to drill deep to get below where organic destructive agents can get to. So I mentioned Mars is bathed in ultraviolet. So you need to drill about 1 millimeter to get to where the ultraviolet can get to. You need to drill about 1 meter to get below where oxidants can get to. So things like perchlorates in the surface, which you'd like to get below to do your drilling. And then below about 1.5 meters to get below where ionizing radiation can get to. So I mentioned the thin atmosphere of Mars. That means the radiation can get to the surface. And so we're going deep enough down to be able to get a pristine sample. That's the idea, to be able to analyze that. And we need to drill 1.5 meters. So we had a student a few years ago working on this, and so he did some calculations and came out with the idea that 1.5 meters actually, yes, was a really good, and 2 meters is what we're drilling. So we'll be able to get below where that modeling showed that we needed to get to. So that's really good. So 2 meter drill and analyze the samples. Okay, so where are we landing? We're landing in a place called Oxyoplanum. So it's a different area to where the Jezero crater where Perseverance is. So on the map of Mars, this is again the low regions on Mars going through middle to higher altitudes. This is the southern hemisphere here. That's the northern hemisphere at the top. And just in this sort of region, so where Perseverance landed is over to the left here. But this, you can see, this is in between the low regions on Mars where there might have been an ocean and with water on the surface, and certainly the signs of water having played an important role here. Again, clays on the surface are very important in the evidence for that. And then the higher altitude regions there are shown in the greener colors. But so we're landing on what looks like it might have been a beach, with the sea lapping onto the shore and so on. So it's a good place to be. And it's also an outflow valley, outflow region from this Cocoon Vallis area on Mars, which means that material would have been brought from a wide area into this particular area to be able to look for potentially signs of life there. So a very exciting mission with UK involvement. And this is the complete list of instruments on the rover. So on the left-hand side, we have the context instruments. So with those, we're setting the context, the geological context for what we do on the surface. So PanCam, that's the one I'm in charge of, is shown on the top left here. Then we have ENVIS, which we're currently building, and then WISDOM, which is a subsurface sounding radar, and then CLUPI, which is a close-up imager. There's also a little spectrometer, visible and infrared, in the drill itself. This is the thing in the middle here. Then on the right-hand side, these are the instruments which will actually analyze the samples. So micrometer is a visible and infrared spectrometer. The Raman spectrometer, with that, you fire a laser at a sample and look at what comes off. And with that, you can do good mineralogy. So there's involvement from University of Leicester, but also Rutherford Appleton Lab and Oxford University in that instrument. And the Mars Organics Mass Analyzer, that's the thing which will actually look for signs of organics and do, for the first time, it's doing this type of measurement, actually chirality. So that's looking at left-handed and right-handed molecules. And so you might remember from schoolwork about chemistry and biology. So so some of those is one of those is used by life and one not. So left-handed and right-handed molecules are very important. That's the first time that will have been done on Mars. So very exciting. So as I say, I'm the lead of this, but we have a big team working on this. ENVIS is led by my colleague Matt Gunn from Aberystwyth University, but we're helping with the build of that, and we'll see some more about that in a minute. So this is the PanCam, the panoramic camera system. So this is the sort of science eyes of the rover, and that's been built 12 miles away in MSSL. At least we put it together. The cameras themselves, we have 2 wide-angle cameras, each of which has a little filter wheel, which we built and added the filters. And then the cameras themselves come from Switzerland of that. The high resolution camera, which is in the middle here, that comes from Germany. So it's an international team working on this, and I'm lucky enough to be the lead of this. And at the bottom of this, we see the different institutions in the UK and elsewhere involved in PanCam. And this is our logo, you know, a nice logo showing a filter wheel going around. So the idea of the filter wheels is to split light up into its constituent wavelengths, and of course use that for analysis of the geology and indeed the atmosphere. So the other instrument which we're currently building, and the team are working really hard on this, the same team that helped us to build PanCam is helping to build ENVIS. This is an infrared spectrometer, so this is one of the things we had to substitute when a Russian instrument couldn't fly anymore. So we had to very quickly in the UK, you know, we made a proposal to replace that instrument, because this really adds to what PanCam can do in the visible. We do the very near infrared, but we're going to the further infrared now with the infrared reflectance spectrometer, ENVIS. So ENVIS, and I'm told by my Welsh colleagues that it's pronounced ENVIS and not ENFIS. It's Welsh for rainbow, and so the idea is to split the infrared up into its different wavelengths and measure that. So there's a nice addition. So the team are working really hard to do that at the moment. We've only been working on it about a year. This is very quick in usual space terms, and the flight model is due actually next year. So so we will be. The engineering team are working extremely hard on that at the moment. Okay, this is PanCam is ready and built, so that's why the team can now build ENVIS. So PanCam on the rover. So this is the rover here, which was going at the time of this picture, going through its environmental tests in Toulouse. So having been built in Stevenage, it and we delivered PanCam to it. This was PanCam in our clean room at MSSL. That's it on the top of the rover. So the whole thing went to Toulouse for some testing and is now actually in Turin, which is where the prime contractor of the mission is, tantalizing in Italy, in Turin. That's where the rover is, waiting really for launch in 2028, having a few modifications done to it and so on. But this is nice because it points out where PanCam is at the top of the mast, 2 meters above the surface, and with our widely separated eyes, 50 centimeters apart, we can get really good stereo reconstruction in the near region near the rover. So this helps us to decide where to go next and where to drill, and also the high resolution camera. So there's some additional things. So the calibration target, we need to get the colors right. So the calibration target sits on the front of the solar panel here. The fiducial markers, that's to get shapes right. Those sit on the side of the rover. And then we have a rover inspection mirror to look underneath the rover itself using the high resolution camera to see signs of rocks, obstructions underneath the rover. So these are the filters, and I'm always excited to show this. These are the actual filters going to Mars. These are the things which will be looking at the Martian surface. And so the left filter wheel is here, the right one is here. The wavelengths are shown there. We have 11 filters on each of the wide-angle cameras. And with this, we do geology and also atmospheric science. So the geology, we're looking at reflectance spectra, so looking at how sunlight reflects off the rocks and looking at the colors of them. And with that, we can do some mineralogy. But we need to go into the red to do that in more detail. That's why ENVIS is on board. But the choice of wavelengths here was done by somebody who was a PhD student many years ago. She's now a senior lecturer in St Andrews University. But we've involved students at all levels on PanCam in this. So we can also, as well as geology, we can do atmospheric water vapor measurements. So there's some of the filters are narrow, you can see here, and these are solar filters, so 925 and 935 nanometers. So the 935 is an absorption dip associated with water. So we can look at the sunset on Mars, and with that, knowing what the dip is, doing a measurement in the continuum of the spectrum nearby as well, we can actually work out the amount of water in the atmosphere between the sun and us. So we can get some information about the atmosphere of Mars. The color high resolution camera, of course, provides rock texture as well. So with that, it's a very complex camera system with lots of really good scientific outputs and really helped by NVIS as well. So this has been tested for some years now. This is an emulator which was built at Aberystwyth University again. So Aberystwyth University PanCam emulator. We can see the wide angle cameras, also a high resolution camera on this. This has been all around the world to different sites which are something like the right geology for Mars. So it's been to the Atacama Desert in Chile, for example. That's it on the top right here. This particular picture was in Iceland. Again, some good Mars analog sites there. It's been to other analog sites as well. So we've done lots of field tests, and there are more planned as well now with the extra time before launch. On the bottom left, we can see some of the data we can get from the really good stereo. We can get a digital elevation model, so where the sort of height map near to the rover. And onto this, we can add the geological filters like dip and strike. This is to do with sedimentary rocks and following particular levels within that. So with that, you can work out the history of the rock formation in the region. In the middle, this is an example of some composition work. So by using those filters and looking at ratios of them, you can work out what minerals are there. So you can see there's sulfur here, gypsum, basalt, all sorts of different things which you can tell the difference between. And so with that, we can work out more about the geology of the landing site. So we delivered the instrument in 2019, and this is the first image actually taken in the Airbus clean room in Stevenage. And so this is PanCam at the top of the mast. This is a colleague of mine holding up a piece of paper in front of the camera, and the piece of paper says, "Hello, Mars." So at some point, we hope to get this to Mars, and so this was our first image, actually getting all the data through the rover systems, etc., back to our analysis tools. And so this, of course, is black and white. We can look at one color at a time. You can put the colors together, but this is just the first image which we took, which is gives us a nice image. So we've done lots of tests on the rover since then. In fact, there is a Mars terrain simulator, as it's called, in Turin. This is shown here. This is the rover, and you can see this is being held up by ropes, sort of. That's kind of to help simulate the gravity on Mars, which is about a third of that on Earth. And we can do drilling tests and so on. So this was done a number of times already. And recently we've had some more tests in this region, in this facility, to test the landing system. So that's some exciting things which we'll find out the results of that at a meeting next week. This is a 3D flyover showing the terrain in that Mars terrain facility, just showing you the 3D reconstruction with the rocks there. So you can get an idea this is flying over quite nicely. So this wide separation actually gives us really good stereo reconstruction, as I said. So it's all working fine. Other tests have been done. So with the drilling, for example, so this was done in February 2023. And you can see this is the drill, drilling from underneath the surface in this Mars terrain simulator, and putting a sample into the what's called the analytical drawer. That's the thing on the side of the rover, which is allows you to ingest the powder into the rover. So, and now you see it, now you don't. So it was not there, then it was there, then it was not there again in this test. So that shows you this that sequence. Okay, so this is a little bit video about the mission, which I'll just play. So in 2028, ESA will launch its most ambitious exploration mission. So that's the 7 minutes of terror as you descend through the atmosphere of Mars. Get it to the surface. So the Rosalin Franklin mission going in 2028. Okay, so we're still doing mission simulations and things like that to make sure the team are together and ready. You know, obviously we've had a delay in the mission, so we have to make sure that everything will be ready for when we go in 2028. Make sure the personnel are the right people and so on. So we keep people busy with both science working on other missions, but also working on simulations to do with this one. So this was a mini sim held in November 2024. The next one is actually going to be next year. So these are some of my colleagues in the operations room here in Turin, and using PanCam data to navigate the rover in that simulation. So just to finish off, so the missions which are going on at the moment, so Hope, Tianwen-1 and Zhurong. Zhurong has now stopped working, but gave some interesting data. But Perseverance and Ingenuity, again, Ingenuity has stopped working, but all those arrived in 2021. The samples are already cached by the Perseverance mission, ready for the Mars sample return. We hope that will happen. And this decade, the Rosalin Franklin ExoMars rover will be launched to provide a really important new dimension, drilling 2 meters underneath the surface. I've tried to convince you why that's important. So still, you know, we do think that's important to actually drill deeper than the current rovers can. And at our laboratory, we're leading PanCam, but also helping to build ENVIS. So I will stop there and see if there's any questions. Thank you very much for listening.
Thank you very much. It was really fascinating talk, and thank you for sharing your work. I think you have to keep the mic because we have only one mic.
Okay.
So anybody who has a question will have to shout out, and we'll have to repeat it, unfortunately, for the line. But does anybody have a question? Go ahead.
Are there any instruments?
Okay, yeah. So the question is, are there any instruments which can conclusively prove there's evidence of life on Mars? Well, the MoMA and the combination of the other instruments is a good combination to be able to do that. So we're looking at the signs of life and habitability. We're looking at chemical markers for life. So we're hoping that that will give us something which we haven't seen before. So very complex organics. Some of those have been seen already, but looking for evidence of life. Conclusive evidence. We hope that with this, you know, obviously there will be debates in the scientific community as to whether we find things or not. I think one of the key things which we can do with this is the chirality. Nobody else has done that before. And so that is the thing which makes this mission, one of the things which makes this mission unique, as well as being able to get the more pristine samples by being able to drill. So with that, you know, that will be the evidence that we're looking for. So it's chemical evidence for life. There's a scoring system for the habitability, which I didn't have time to go in for. But with that, we hope to be able to quantify how certain or not we are of signs of life. But, you know, of course, the combination of this and Mars sample return, if that brings the samples back, then we'll be able to use Earth-based laboratories to analyze those samples. The Chinese also are planning a similar mission in 2029, so maybe that will bring samples back as well. So, but with that combination of what we can do from drilling underneath the surface and what the more surface instruments and the, you know, the samples which will come back and using really big facilities to analyze those. Hopefully, amongst that, there will be the body of evidence. But the chirality, for me, that's one of the key things which we're able to do, which others are not able to at the moment. But of course, if you bring the samples back, that might be one of the first things you do as well.
We seem to have found a mic, so.
Oh, good.
Okay.
How much analysis are you going to be able to do locally, and how much has to be done remotely? Here,
Yeah.
remote and local being
With
Mars.
with our mission, it's all local. So I mean, the cameras in a sense are remote sensing things, because you can look in the far distance and see other rocks and so on. But it's all being done on the surface, and we send the data back by radio. But bringing the material back is very important for potentially looking for evidence for life as well. So I mean, I think we obviously do need the sample return in addition to what we're doing on the surface. But what we can do, is look at this this deep subsurface, which the other missions are not doing. So that gives us our unique selling USP in there of this mission, which is still valid, and it will still be valid in 2030 because nobody else is actually trying to do this. So it's still a unique mission. But yes, it can only do the analysis on board using those 3 instruments on the right-hand side of the payload thing to actually analyze the samples themselves. We can look at the remote sensing with our cameras as well to make sure we're drilling in the right place. But it's those samples and analyzing those and sending the data back. That's where the evidence could be. But yeah, I mean, it's a good question about the definitive. Can we be definitively sure? Obviously, there will be a body of evidence which we build up as where these have come from exactly, and whether it could have been associated with life. But yes, we're doing all the measurements locally for this. Bringing the stuff back is obviously very important too, though. Yeah.
I'll keep going up towards
Yeah.
the back. Do this.
Yeah. How does the drill extend to 2 meters?
Yes, good question. So I've got a little video on that. I'll see if it might help. There's a couple of videos here, but one is about the drilling in detail. So I'll maybe leave that running while talking about this. But so you basically have extension rods, and so you can see this is the drilling in detail. So that's the interior of the drill, and there's a mandrel which rotates and pushes the drill into the ground. It's a bit slow, the video, but the real thing will be a lot slower than this. And we're putting together different extension rods. So 4 extension rods really to get down the 2 meters to be able to get the to be able to get the sample from there. So the mandrel then ascends to collect and add an extension rod, and you can see that going down, and eventually we get to 2 meters. I think somewhere in here it says it takes about 4 days to do that.
Yeah.
So it's not immediate. This is obviously really sped up, but about 4 days or 4 sols on Mars to be able to do that.
How many drill holes are you expecting to do?
We're expecting to do, I think maybe 10 altogether and 2 really deep ones. So we've got to choose the place where we drill really importantly, really carefully, and that's why we have the other payload on board to be able to choose those drill spots in detail. That's basically how it works of adding extension rods, because obviously the thing on the front is only about 0.5 meter, and so we're adding extension rods to be able to get down the 2 meters, and then we get the sample and bring it back and put it in the analytical drawer, as it's called in the it's a bit slow. Yeah, oh yes, okay. The imaging spectrometer in the drill tip looks at the sort of local geology underneath the surface. So with that, we, as well as doing the geology on the surface, we have the subsurface geology as well. And then the sample is brought back, put in the analytical drawer and analyzed by the instruments. Okay, thank you.
Thank you.
With the chirality of the determining the chirality of the rocks,
Samples, yeah.
samples.
Yeah.
Are you able to tell whether it's a race mix so that they're equal left and right, or whether it's biased towards the left enantiomer
Yeah,
actually on the machine?
I believe we can.
Yeah.
So yes, it is able to do that. So the way this instrument works, it's a gas chromatograph mass spectrometer. So it heats up the samples, and so you can get the it does the mass analysis, but then also the chirality analysis is part of that as well. So I think we can tell the ratio between the left hand and right hand.
Oh, that's good. So that'll be quite a good
Yes.
indicator, won't it? Yeah.
Yeah, absolutely. Yeah, yeah.
Going up this side, I see you as well, so we'll get around there.
Yeah, on your sample collection side,
Yeah.
you showed a group of samples called witness samples. What are those?
Right. Which one was that? Do you remember which slide that was? Oh, witness samples. Is that mentioned here?
Way before then.
Okay. It's on the Perseverance, this slide.
That's it.
Okay, yeah, right. So the witness tube. So this is there's some atmospheric samples which they've taken, which are mentioned here. The witness is to, I think, to make sure. Yeah, I can't remember exactly what it is, to be honest, but it's to do with it's a sort of blank measurement, as it were. But I can't remember exactly the technical or the suggestion there. But yes, it's a witness to basically help to show that the other measurements that you're making are correct. I think it's to test the inside of the gas chromatograph mass spectrometer. Actually, is sort of a blank sample which are used in these types of instruments. I think that's what it is. Yeah.
Well, I guess for fairly obvious reasons, we're looking for life as we know it.
Yeah.
And I just want to ask, it might be an absurd question, but I just wonder, what is our definition of what life actually is?
Well, yes. I mean, people are working on this, and indeed, for how life started on Earth, we still don't know the answer exactly how it started on Earth. We know it's about 3.8 to 4 billion years ago. But yes, there are other types of, in science fiction especially, ideas of silicon-based life and so on, which are there in the literature. Chemically, it could happen. But the best thing we can look for is life like we have on the Earth. And so that's our only example of any life which has actually worked. And so that's the best place to start looking. And so the instruments are designed to look for that sort of life and the biomarkers associated with that sort of life. So we can look for, I mentioned amino acids, but also things like phospholipids, which are to do with cell wall boundaries, that sort of thing. So the building blocks of life, which go into bigger samples of life. But yes, other life forms are theoretically possible, but our best chance is to work with what we've got and what we know about. So that's why it's been designed in this way. But of course, potentially there could be other types of life, and something like the telescopes looking at extrasolar planets could, in principle, find different stuff, by chance. And so looking for that is a possibility too. But yes, interesting question. Thanks.
I might
Any
be
others?
straying into politics here, but
Oh, hello.
how freely is the data from the various probes shared?
Well,
The countries involved don't necessarily see eye to eye.
yeah, we have international conferences. So, for example, the the American data is available just about immediately. We want to make the PanCam data available immediately. We're working with ESA to do that. Normally, there is a sort of proprietary period for data in Europe, but actually we're trying to go beyond that with this mission now. Other missions, the UAE mission, for example, that's international. There's lots of US involvement, and it's an international effort. China as well. I mean, we've had Chinese scientists visiting and us visiting China as well to discuss the data. And again, international conferences discuss the data relatively freely. So data exchange and we're sort of using one mission to design the next one in some ways in this. There is something called the International Mars Exploration Working Group, which looks at the scientific justifications for each mission and decides what can be done internationally. And so the missions are sort of working on that basis. And so we're standing on the shoulders of giants, as always in science, like Rosalin Franklin especially, to be able to get to what we can. So yes, it's an international community. But geopolitics did come into it with our launch. So I had hoped it wouldn't necessarily be an issue, but of course it was. You couldn't have a big Russian rocket launching our rover, unfortunately, to Mars. It wouldn't have been right at the time. So the European Space Agency and the governments which make that up decided to stop working with Russia at the time that invasion happened. But in fact, I mean, the story about that, we were doing the calibrations associated with the instruments, especially the camera alignments and infrared spectrometer alignment and alignment with the navigation cameras and so on. At the end of that week was when the invasion of Ukraine happened. That was exactly the time we had hoped to be putting everything together and sending to the launch site. In fact, that process had started. Then the invasion happened and we had to stop. So, we now have to work again with the States. But this mission has been a roller coaster ride, to be honest. I mean, first of all, it was going to be Europe by itself. Then it was going to be Europe and NASA. Then it was going to be Europe and Russia because NASA ran out of money at a key point. And now it's back to, having gone through the Russia thing, it's now Europe and NASA again. So this is what we're hoping for and for launch in 2028. But geopolitics, unfortunately, did get in our way with this mission, but we hope for the best in the end. Sorry, I have to walk. Oh yeah.
I'll take this one first,
Yeah,
and then I'll come down. There you go.
Just on this slide, could you elaborate also on the empty tubes and the Three Forks cache?
Yeah, well, great question. So the Three Forks cache that's an area where some of the samples were stored for a potential sample collection rover to bring it back. What was the other? Oh, the empty tubes. So again, that's to test the analysis on Earth. Make sure nothing happens to the sample tube itself on its way back to Earth. So some empty samples and empty chambers are needed to do that. The witness tubes, again, similarly, as I say, I don't know in detail exactly what these are, but these are what's listed on the website as what have been brought, what have been stored ready for bringing back. But it's to do with making sure the measurements are right, basically, in a nutshell.
Yeah, just what kind of substances are you expecting to drill through? And what's the hardest substance that your drill will actually bore through?
Well, it's been tested in a number of different environments. So if I go to this one, for example, so we're drilling sort of relatively deep, drilling basically through soil for a start, or regolith, as it's called, and so that's relatively soft. But the drill has been tested with a number of different thicknesses or hardnesses of material to be able to get it to be able to get good results. And so that's part of the reason for the drilling tests in the Mars facility in Turin. So making sure that we can cope with the right sort of the different stresses. You imagine when you're hitting a hard rock, it's more difficult to drill, but you're drilling slowly. So the idea is to, the videos you saw really speeded up. Drilling through a range of hardnesses enough to cope with what we might expect on Mars. So it's been tested in those different environments. Okay.
One more.
Yeah.
Oh, yeah, you've had a question.
The cameras forming the stereoscopic pair,
I was sort of assuming that they were monochrome. Are they monochrome? Or
Yeah,
colour?
they are monochrome.
Because you
So,
had two filter wheels marked left and right, but they
Yes.
had different filters in. I'd have thought you'd want the same filter wheel over both cameras, so they're both seeing through the same filter at the same time.
we've got some which are replicated between the two, but others which are different. So one of them is more towards the geology, one's more towards the atmosphere. But well, actually, it's been, so we've got red, green, and blue on each of them, so we can get color from either camera. We've got some of the geology filters. There's, I think, one which is replicated on the other one, so you can get a good red image, and that's where some of the mineralogy is. But others are distributed between the two, so you've got a combination. But it's sort of, again, the student who helped with this helped us to decide which filters should go in which of the two filter wheels. So the solar filters, for example, are on both, but there's only one on one of them, but it's not a very good explanation. But so some of them are replicated, some are not, and it was to sort of try and minimize the amount of moving of the filter wheel which we needed to do to get a reasonable spectrum. I think that's the right answer.
Okay, thank you.
We'll leave it there.
Okay.
Thank you so much. We very much appreciate you coming to see us, and we appreciate you in the usual way.